So hello everyone. Welcome back to the machine learning lectures. Today we'll be looking at cross-validation. So let's see what's on the agenda for today. So first of all, there was a question that we left in the last class, like how do you choose the value of K in KNN algorithm? Then we'll talk about cross-validation. So cross-validation is also one of the way you decide your hyperparameters. So that's where cross-validation comes in this whole picture. And then we'll talk about cross-validation. There are 4 types of cross-validation that we'll be talking about. So the 4 types are holdout cross-validation, K-fold cross-validation, leave one out cross-validation, and stratified K-fold cross-validation. Fine. So let's start. So how do you choose K for the K nearest neighbor algorithm? Just So there is a rule of thumb that is used by data science community in general, that you choose the K as the square root of number of data points that you have in training set. And people have experimented with this and they have realized that this particular K works well. Obviously not always, but sometimes, mostly if you start your K nearest neighbor algorithm with K set as square root of total number of data points, it's a good start point. It's not definitely going to be the best classifier, but it's a good start point to start with. So you can start with K is equals to root n. Fine. But again, this is a good starting point, but it's not an optimal number of neighbors that you should be looking at. Another way is you can do grid search using the cross-validation. So what is the meaning of grid search? So grid search is basically nothing but a for loop. If you have watched the Python lectures, you will know that what is a for loop over a range of values. Okay, so you will come up with some ranges of K that you want to explore, and you will basically train your KNN. So there is no training involved, right? So you can just store that in memory and you can just do on the fly computation. And that's why, cross validation is a preferred method. We'll come to what is cross validation. Just know that this is one of the methods to find the best number of K. And for each K, you will do the cross validation and choose the K which gives you the best CV performance. Okay, so 2 things that we have to look out is what is cross validation and what is the cross validation performance. So just understand that we'll be doing something with the K-nearest algorithm. You can actually apply it to any classifier you want, any regressor you want. But for KNN, it's simpler because you don't have to train a model. In cross validation, we have to train models multiple times and we'll see how. But uh, but in KNN specifically, you don't have to train the model, right? We discussed in the last class that it's a memory based classifier. So it will just learn all the data points that you have in the training. And whenever you have a prediction value coming in, it will just look at those numbers of neighbors and it'll start calculating or it start giving you the prediction value outright. It doesn't have to wait or it doesn't have to train for any search time. And hence you can use cross-validation to do a grid search for your parameter K in KNN. Obviously, K is a hyperparameter here. Okay. So in general, cross-validation is also used to do hyperparameter tuning. Hyperparameter tuning is that what is the what's the best or the optimal value for your particular hyperparameter. When you do that specifically and you train multiple models and then you decide on one value of that hyperparameter, you say it's hyperparameter tuning. Right? So you can use cross-validation also. We'll see how to do cross-validation. So what is cross-validation now? Okay. So cross-validation is a technique which we use to evaluate the machine learning models by training several models on subsets of available input data and evaluating them on the complementary subsets. Okay. So there are 2 things that we do over here. So first of all, this is a generic pattern. Suppose you have all of this as your training data. This is your training data. So what you will do is you will divide your data into two parts. You will call this as train data and you will call this as validation data. And this is something that we saw in the introductory lectures. What is validation? What is training? Now what you will do is, now this is your training data because you don't usually have the test data in your hand, right? Your model, whatever you are building, is going to go in the production setup. You are going to finally deploy it somewhere. So when you're just building your model, you usually don't have the test data with you because that's kept for the last. That's kept for till the end. Once you finalize the model, then only you can use a test set. But how do you evaluate your model in between? Suppose I have trained a model, but I am not doing any evaluation. What will happen is when it goes into the production setup or when I deploy my model, I don't know how it's going to perform. If I have a customer, I have to give that customer some guarantees how this model is going to perform in the production setup or when I deploy that model in their system, right? So for that, what we do is we do validation. And usually you will see cross-validation is the most preferred technique in industry to get an estimate of how the model is going to work in a production setup. Obviously, this might not be always the case that uh, uh, it works exactly like that, but it gives you good guarantees that, okay, at least this much it will be able to do. Fine. So what you do is you divide your training data into two parts, and one part you will use for training, other one you will use for validation, and you report this validation accuracy or whatever metric that you're computing as your performance, that okay, I'm expecting this much of the performance in the production set. Fine. Now this can be used for both classification and regression problems. So we'll see how we can use that. And it's used for estimating the test performance and hyperparameter tuning. So it's just to give you an estimate of the test performance, right? So not exactly it'll tell you how it's going to perform in the production setup. It'll give you an estimate. Okay, this much it should be able to perform, right? And we'll see how that happens. And as I said, it also helps in hyperparameter tuning. So whatever hyperparameters that you have, you can set a value of those hyperparameters by using cross-validation. Fine, if things are not clear, it'll become clear in a while, like how it's going to help in hyperparameter tuning. Okay. So we'll now discuss about the different types of cross-validations. Any doubt till here? Any doubt? No? Clear? Fine. Okay. Now let me start talking about holdout cross-validation. Okay. So what is holdout cross-validation? This is the simplest and the most common technique. Like this is something that you will see everybody doing, and this is something that we already talked about in the introductory lectures. Okay. So what you will do is you will divide your data set into two parts. So this is your data set, whatever data set you receive for training. Okay. You will divide it into two parts. So this part, the smaller part, you will call as validation set. And this part, the bigger training data or the bigger chunk of the training data, you will usually use it for training. This is training set. Okay. So usually you will use 80% of the data for training and 20% of the test set for validation. Fine. So this is a industry norm. You can actually choose a different number. I myself have worked with 70-30, 65-35 as validation set or test set or training set. Fine. Now what you do is you sometimes people like to call it test set also. But in this context, we'll call it validation set only. So I'll just remove this. This is validation set. Some people call it test set also, but usually we have a third chunk of the data set that we keep out till the last to get an actual estimate like how it's going to do on completely unseen data. once we have already decided on the model, which model we are going to use. So I will use validation set as a term, and I'll correct while going through these lectures. If I anywhere by mistake I've used test set for the validation set. Okay. And then you will just use the this result, whatever you used of the validation set is basically an estimate of how model is going to perform in production or on test set, on actual test set. Okay. So now how will you use this cross-validation, holdout cross-validation for choosing the best model? Okay. So what you'll do is, so you will use model 1. Okay. So you will use the same chunk of the data. Suppose there is some data that is given. Here you are using, say, linear regression. So you'll do the same thing. You will divide the data into 2 halves. So this is your valid set. And this is your train set. Okay. You will train your linear regression. You will get some estimate. So CV linear regression will be some value, say V1. Fine. Then you will train another model, which is model 2. Let's say you decide to use SVM for this. Or let me say neural network for this. Okay, again, you will use the same test set, same train set and the validation set. You will compute the estimate of your model on the holdout set, whatever you have kept here. So this validation set is also called holdout set. And hence it's called holdout cross-validation. So this is holdout set as well. Now you will compute the CV error as neural network, and this will be some value V2, right? And so on, you will do it for how many ever models you want to try. Some model N, right? And some configuration of that model, maybe neural network with 1,000 layers. We don't know. Okay, so there'll be another CV and then some 99 configuration of this, which is V100, Vn. Right, so you are now getting n estimates of different models. What you'll do is you will choose the best value. Suppose this is error, or this is loss, or say this is AUC. Okay, not. Let's say this is mean square error because you are doing the regression. So suppose this is mean square error, right? So you will choose the best value, which is basically the lowest mean square error among these. And you will finalize whichever model is giving you the lowest cross-validation error, you will finalize that as your best model. You'll say, okay, this is a model I will take ahead and I will deploy this particular model in the production setting. And this is going to be used in testing, or this is going to be the model that will basically be used on the test set, which already you must have kept out for getting the final evaluation of the model. Fine. Clear? Yes. Any doubts here? Okay. So usually we use this method of holdout cross-validation on large data sets as you are doing only training once. Okay. And you will see what is the meaning of training once only. Here, what you're doing is that you're just creating 2 chunks of the data. One is called training set, one is called validation set. But in the next versions of cross-validation that we are going to see, we don't just create 2 splits or 2 chunks. We actually divide them into multiple chunks, or we call them folds. And then we train multiple models in one iteration of cross-validation. Okay, so here, because you are using, suppose you have a very large data set, right? If you have a very large data set, training time also increases with the number of data points that you have. Hence, if you have a very large data set, you will prefer this holdout cross-validation method, over other methods, because you don't have to train your models again and again and again. Fine, and it will become clear once we see what is the meaning of training models again. But there are some disadvantages of using holdout cross validation. So it can happen that whatever split that you created is not a true representation of your data that you have in training. Okay, suppose this split is not random. Suppose I have this particular data set over here, right? And suppose this was sorted data. Okay, so suppose there was student marks data, and this data, suppose this was sorted already. So this is sorted in this increasing order, sorted. Okay, and I create a chunk like this. So what will happen is, here in the validation set, you will have students who have higher marks or lower marks, depending on what kind of sorting you have done. So this will have students with higher or lower, highest or lowest marks. Depending on the type of sorting you're using. And this will have the lower or the higher marks or whatever, right? The rest of the marks, right? So now this validation set is not a true representation of the data distribution, right? Because here you will have students say all of them who have marks less than 90. Here you will have students say who have marks greater than 90, right? So if you are going to train on students who have less than 90 marks, and you're going to train on students who have greater than 90 marks, sorry, you are going to validate on the students who are going to having more marks than 90, then this is not the best estimate of your model. You should ideally just equally or evenly distribute your data, so that whatever distribution of marks you have in your training set, it's actually maintained in both, right? But it can happen that when you do a random split also, you might reach a rough spot, or basically you will reach a validation split on a training split, which is not evenly distributed, or where the either of the set is not a good representation of how your full data is. Okay. And another disadvantage is that we have over here, we said that this is an advantage that we have to train model only once, is that because the model is only tested once, it will not give us good guarantees. It might fail to give us good guarantees as you're just testing your model once. Okay, and we'll see why other variations like K-fold cross-validation is better, right? Because you will be testing your model multiple times. Fine. Any doubt here? This is very simple actually. Okay. So let me give you the disadvantage. Okay, so suppose that this is all of my training data that we had, right? Now I created a split, and it so happened that in this particular split, all the Sphinx cats over here, right? All the Sphinx cats move to validation set, and all the cats which have fur, they are in my train set. Now tell me, if I train on this particular train set and I try to estimate or try to predict something about the cats over here, do you think the model will do good? Suppose this is the only training data that you have, right? Or say any metric for that matter. Do you think this model will do well? No, right? So it will not do well because it has not seen the data for Sphinx cats, right? So there is no Sphinx cat in my training set. This is a very different kind of a cat, something that we have seen in the introductory lectures also. So it doesn't have a fur, right? And here my model is seeing fur only, right? Now suppose you're going to train a dog versus cat classifier. And this happened to be that the distribution of your cat class, that all the furry cats were in the train set, and the cats, Sphinx cats, which don't have a fur, they move to validation set. So it can happen that your classifier, which is classifying cat versus dog, might not classify these particular cats into cat category. It might categorize it as a dog. It can happen, right? So in that case, this is not a good evaluation. This is not a good split indeed. And whatever estimate that you will get of your model will not be good. It will be kind of biased because you're biased in the sense that it will be bias is not from that bias variance term. Okay, bias means that it's biased because your data distribution is uneven. Fine. So here you have all the furry cats. Here you have all the cats which are not having any fur. So this will not do well. So you can reach one rough spot like this before doing the cross validation. So it's a good idea to always check the distribution. Always check distribution. Label distribution. So basically distribution of labels, or say features also, like how the features are distributed. Like you can compute statistics like mean of this feature in training set and mean of this feature in the validation set, and see if they are looking okay, if there should not be way off. Okay. So always check the distribution of labels and features before doing, after splitting, and before doing cross validation. And then only proceed. Okay. Another thing is, so model is tested only once, hence might not give good guarantees on the model performance. Okay. So because you test model only once, and suppose that you reached a split like this, right? Here you can see that these kind of cats, right? I don't remember what is the type of this cat, but you can see that these kind of cats are very much in the data set, right? This particular cat is of the same type. This is also of the same type. This is also same type. This is also same type. This is almost also, let's not include that because this is white. So I have 4 data points which are of the same type as a validation set. So there are 2 things playing out here. So the split is not good. Also, I am not evaluating things on, all of these other cats. The split happens to be like this, that these 4 cats made to my validation set, and I happen to have these kind of cats too much in my data set, in the training set, right? So definitely my model is going to perform better over here because it has already seen these kind of cats over here. And because I'm doing validation just one, or model testing only once from this particular data split, so I will think my model will do awesome in the production setting. But what will happen is it'll fail for, say, this kind of cat. This can fail on this particular cat because there's just one example of a black cat. Sphinx cat also you can fail again, right? This also, this ginger color cat or this particular cat, you can fail, right? But you're doing just the evaluation once. So you will think that, oh, my model is doing nice. Maybe there's like 100% accuracy over here, right? You will think that this particular model is best. Let's deploy it in the production setting. And you're not really getting a very good estimate of how your model is going to do in the production setting or the deployment setting or on the totally unseen data. Fine. Here. Okay. So what do we do? Okay. So what do we do is K-fold cross-validation. Okay. So this is another very simple technique. So in K-fold cross-validation, you will basically try to overcome the test only once bottleneck. Okay. So you're basically testing your model only one time, right? So we are going to try to overcome this disadvantage. And it introduces a new way of splitting the data. So this is just one new way of splitting the data, and we'll see how this helps us. Okay. This technique actually minimizes the disadvantages of the holdout method. Okay, let's see this. So this is a very simple algorithm. What you do is you split your data into k equal parts, which are called folds. Okay. Suppose this is my training data or all the data that I received for the training. So what I'll do is I will divide, say let's k is equals to 4. Okay. So I'll divide it into 4 equal parts and I'll randomly do this. Okay. Now what I'll do is in the ith iteration, I will choose I fold as my validation set and rest as my training set. Okay, so this is 1, 2, 3, and 4. Right? So say my first iteration is going on. In this, my validation set, and here is your training set. So say your first iteration is going on. So what you'll do is you will use this fold one, which is I, this here, right? You will use it in the validation set. Okay. And remaining folds 2, 3, and 4 will comprise your training set, and you will train a model, right? And we'll call it model 1, right? And we'll get an estimate of the performance CV1. Okay. Then you will train the second model where you will use the second split as this particular split. So I'll differently color it differently. So you will use the second split for your validation, and rest others you will use for. So you will use 1, 3, and 4th split in your training. Then you will make a model 2 after using this particular training data, and you will get some value CV2, which is like your estimate of how this model is doing on the second split, right? Then again, you will train third model, in which you will use your third split as your validation set. So this is your third split over here, and you will use 1, 2, and 4 as your training sets. Like you will add them up, all the data that is there in the first fold, second fold, and the fourth fold, you will add them up. You will get an estimate CV3, and you will do fourth. Obviously you're training here model 3. Here you will use this particular chunk. So in this particular case, I have not divided them equally. You will always divide them as equally as possible. Okay. So if there are odd number of data sets or if data points, you basically try to keep them as equal as possible. Sometimes one particular fold might not have those equal number of data points in it. That is fine. Okay. So here you will have fourth split in your validation and first, second, and third split in your training. You will train model 4 and you will call it CV4 as your estimation. Okay. So what will you do? So this is how you do this much part, that you choose the ith fold as a validation set and rest is training set. Train the model on the current training set. So this is basically current training set. All of this is your current training set in every iteration. Save the results of the validate on the current validation set. These are your validation sets for the ith iterations. And then you will save the results of every validation that you have done. Okay, so this is cross-validation, K-fold cross-validation for first fold, second fold, third fold, fourth fold. Okay, so you'll get 4 values. So in the end, what you'll do is you'll take a mean of. So I'll write it here. Estimate. Your error estimate is basically mean of CV1, CV2, CV3, and CV4. Okay, so this basically is your estimate now, right? Now this is better. This is better is because you are evaluating on every data point, right? Every data point is going to be part of your validation set somewhere, like in some iteration, it will be part of your validation set, right? So if some particular fold is performing really bad, you will know that, okay, this is not a good split because others are doing well, right? So you might want to reshuffle your data and create new splits and see how to do that, fine? So this is your test estimate now. And this is what is K-fold cross-validation. You have divided your data into K-folds, and in a round-robin fashion, you're using one of them as the validation set and rest of them as your training set. Clear? Yes. So this is very simple technique. Okay. So let's try to divide this data into 4 parts. Okay. So this is 4 folds that you'll create. So there are 12 cat images over here. So you have 12 cat images. And I'm saying I want to take the K as 4. So K is equals to 4 means every fold has 12 by 4, which is equals to 3 data points. Okay. So in every fold, I'll have 3 data points. So this is fold 1, this is fold 2, this is fold 3, and this is fold 4. Fine. Now, when you train model 1, so the yellow ones represent my validation set and the green ones represent what is being put in training for that particular model. Okay. So in model 1, I will train using fold 2, fold 3, and fold 4. So fold 2, fold 3, fold 4 will be in my training, and I will be evaluating on fold 1, right? Similarly, in second fold or in second model, you will use fold 2 as your validation set. So this is my validation now. And rest others are my training, right? So fold 1, fold 3, and fold 4 are my training. Similarly, you will do fold 3, which is now validation over here. So okay, so what is the meaning of having the same model here? So model configuration will remain same. Model configuration will remain same, will be same. Okay, only the data in every iteration is changing. So suppose here you start with, so maybe we can write, choose one model configuration. Okay, so before doing this, you choose a model configuration and you stick to that. So if you're using a linear regression, you're going to stick to linear regression for every fold. If you're using neural networks with 10 layers, 10 neurons each in every layer, you're going to stick to that. Right? So whatever is your model configuration, you will choose it before doing this and you will stick to it. Stick to it. Okay. Now, if you decide to change your model configuration, that will be another set of cross-validation you'll do. Okay. So this is validation set. This is your, finally, you will have validation set over here. Okay. And fold 1, 2, 3 are in your training. Fold 4 is in your validation now. Okay. So this way, what you have done is you have used all your data in training as well as in, just a second. So you have used all your data in training as well as in doing the validation, right? So you kind of basically used all your data points in validating. You have at least validated every data point at least once, right? So every data point makes it to the validation exactly once, actually. Exactly once, right? So whatever data you have, you are using all of your data, whatever folds you have, all of this data is at least, is actually, is exactly tested once, evaluated once. Okay. So this is how you do your K-fold cross-validation. Okay. Now there are certain advantages to K-fold cross-validation and also there are disadvantages of using K-fold cross-validation. Okay. So K-fold cross-validation is actually more stable in the sense that you are now taking a mean of all these values, right? So whatever you have, even if your one fold behaves badly, your estimate will be an average of that, right? So if all of them are bad, your performance will be bad. If all of them are good, or your performance will show that as a good thing. If one of them is bad and rest all others are okay, then it will show you a little decrease in the performance, but not that much, right? So this is actually more stable than holdout data set because in that you're just evaluating one. So whatever performance you're getting is it, right? Here, because you're taking a mean of stuffs, then it's more stable and trustworthy. Because you're now kind of using all your data for training and testing in some way, right? And also because your training and testing has happened on several different parts of the data set. Fine. Now, what we can do is we can actually make it more robust by or whatever score that we are getting, right? We can make it more robust if we increase the number of folds. Okay. And we test on many data, small subsets. Right now, suppose that we took 4. If I take more subsets or more folds, say 10 folds, right? So it'll be a better estimation of your result or your test. But what do you think can be a disadvantage of this? So if I decide to use 10 folds rather than 4 folds, what will happen is, as you guys have already said it, it'll increase the time complexity, and your time will be more and your computational resources will be utilized more. Okay, and this is just for one model. Suppose you want to experiment with 10 of the models. You want to experiment with different 10 configurations. Now you're going to train some 100 models. Let me make this very clear. Suppose that you have 10 model configurations. Right? So total number of model trained, number of models trained. So if you have, say, k is equals to 4, you will train 4 into 10 models, which is like 40 models, right? Now in this case, you will use 10 into 10 models, which is equals to 100 models. Okay. And your training time increases. Why do you think the training time increases? Let's see the size of the train set and validation set here. So I will find the size here. Okay. So when I have, suppose you have 100 data points. Okay. So what will be the size of my validation set when I am using K-fold? K is equals to 4 folds. So it will be 25, right? This will be like 100 by 4. So there'll be 25 in every fold. One fold will make to validation, rest others will make to training. So there'll be 75, right? So we have 75 data points in training. Now, when I have 10 models, so what is the size of my every fold? My fold size will be 10, right? So 100 by 10 is equals to 10 is fold size. This is the fold size. Fold size for k is equals to 10, right? How many data points I'll have in training? I have 90 points, right? Because rest 9 of the splits will make to train set, right? So what happens is your training time also increases because your number of data points in the training increases for every configuration. Sorry, for not every configuration, for every iteration, your training set is bigger if you have a bigger K, correct? If you have the same number of data points, obviously 90 is greater than 75. So what will happen is your training time increases. So your training process might be really expensive and time consuming. In KNN, it's not a problem because KNN doesn't do any training, right? So hence you can use cross-validation over there very easily. You don't have to train any model, right? And you can do a grid search kind of a thing and decide on the value of K, and hence cross-validation is the preferred method of doing or finding K in KNN. Okay, so this is clear, simple enough. Okay, this is the maths of CV. Okay, so there is a disadvantage that you have to train models multiple times and your training process can be expensive. So your GPU requirements will increase, the time that you're allocating to finalize one model will increase. So it comes with pros, but as well as cons, right? So, but this is still used in production. People rely more on K-fold cross-validation rather than holdout cross-validation because it gives you a better stable estimate of your performance. So whenever you go to your customer, they will usually ask for a K-fold cross-validation to be already done on your model, and you should report those guarantees to your customers and whosoever you are building this model for. Okay, fine. Now let's talk about leave one out cross-validation. So this is again a very simple technique. It's a special case. It's a special case of K-folds cross-validation. Fine. Let's see. So leave one out cross-validation is an extreme case of K-fold cross-validation. What you do is here you set K is equals to N, where N is the number of samples in your data set or total number of data points. Okay. So here you basically every data point is a fold. Okay. And you basically train your model for N minus 1 times and you evaluate on whatever left out data point is. Okay. So if we set K is equals to N, K is equals to number of data points, then it becomes your leave one out cross validation because you're leaving just one data point out and you're training with the rest of them. Okay. So the algorithm is very similar. You have N is equals to total number of training points in your data set. Okay. So what you'll do is from I to 1, you will pick ith data point as a validation set and rest is training. Okay. So how many validation, how many folds, how many data points will be there in the training set every time? Size of training set will be N minus 1. Size of validation set is equals to 1. Okay. So you will train the model on the current training set, which has size N minus 1. And you will evaluate on the current validation set where size is equals to 1, right? And you'll save it in BI and you will take a mean of all those values that you get. Okay. So in this way also what you have done is you have traversed every point individually, right? Also, what you have done is you have almost used all the data. So there is no wastage. For every model training, you have used more than 99% of the data, approximately 99 at least. You have used 99% of the data. So it actually gives you a very good estimate of how your model is going to perform in the production setting. So obviously, there are disadvantages that it will have more time complexity. It will take more time to train. Also, the number of trains that you have to train, the number of trainings that you have to do is as much as number of data points you have. Suppose you have 1,000 data points. So you'll train it for 1,000, you'll train your model 1,000 times, right? But still a more, it's a much better estimate. It's more robust than your K-fold cross-validation. Okay, so let's see one example. Suppose you have only 6 data points in your data sets. So how many models you will have to train? How many models will have to train? So every data point will meet to the validation once, right? So we'll have to train it 6 times. Every model 6, right? 6 times. Okay. You can make a mistake here. Be careful about this. Okay. So 6 times you will have to train your model, which is equals to number of data points that you have. So I have 6 data points over here. So we'll train it 6 times. Okay. So this is your first, this is your validation set. And these rest are your training. So you have in validation set, you have data point 1. Similarly, you have data point 2 in second model. Third model, you have data point 3. In fourth model, you have data point 4. In fifth model, you have data point 5. And sixth, you have data point 6. Okay. So we have 6 validation sets. So you're training 6 models now. Fine. Okay. So now there are advantages to this approach. Obviously, that it actually doesn't waste much data, right? Every model is trained with at least 99% of the data. And we use only one sample from the whole data set as a test set, right? And we are training with the rest of the training set. So approximately 99% of the data is used. Always used in training. Fine. Now, this is also called LOOCV. You will heard people calling it LOOCV. So this is leave one out cross validation, just the abbreviation of that. So it gives more accurate estimates of your true error, then K-fold cross-validation, right? Because now you're using all the data, almost all the data in your training. Hence, it will be more closer to what will happen to this model in the production setting. Okay, and if I have not talked about it already, let me add the point here. What is the meaning of this? Okay. So what is the meaning of this? Okay. So what do we do is once we do cross validation, right? So once cross validation is done, so you could be doing cross validation for various reasons, right? One is hyperparameter tuning. One is used for error estimates. Okay. So once the cross validation is done, you actually train your model using the best setting that you have found. Okay, so what is the meaning of this? So suppose I trained and this is not, I'm talking about not the individual cross-validation model. Suppose I tested some 10 model configurations. 10 model configurations I had. Configurations. Okay, and I did cross-validation on each of them. And I realized that my model or my configuration 7 is best. Let's assume 7 is best. Okay. So what you will do is you will actually train your model using the best setting that you have found and all the data in your data set as training. So whatever splits you were creating were only limited to your cross validation. Once you have done your cross validation and you have decided, okay, probably this particular setting is best, right? So if you have 10 models, say 7th configuration is best. So what you'll do is for 7th configuration, for 7th configuration, you will train your final model that you're going to deploy in your production setting will be basically trained on using the best setting that you have received after doing the cross validation. And you will use all the data that you had for your dataset training over here. So all this data that you had, right? All of these points that you have, you will use all of them for your training and you will train your final model using all the data. And that you will use to test on your test set if you have. Obviously, you would have kept a test set already outside on which you can do your error estimate, or you can do like a test estimate, a final estimate of how your model is doing. Right? And hence, LOOCV gives you a more accurate estimate because it uses approximately all the data, in training. Every fold. Make sense? Clear? Yes? No? Doesn't make sense? Make sense? Clear, right? Fine. Okay. So there are advantages of using LOOCV and there are disadvantages also, as you guys have already pointed out. That now you'll be building N models instead of K models, right? And if your data set is like huge, you'll be training a lot of models. And if you have multiple configurations that you want to try out of your models, then you will be training like insane number of models, right? So that is one estimate, like one disadvantage of having or doing leave one out cross validation. So what we try to do is we try to balance things out between leave one out cross validation and K-fold cross validation. And usually people you will see will use either 5 or 10-fold cross validation rather than using a LOOCV, like an exact like just leave one out data point and doing that. Okay. Another issue is that it has high variance. So what is the meaning of high variances? So whatever over here is happening, right? So you're predicting on one data point every time, right? So what you'll see is that this particular model or whatever, not this particular model, whatever leave one out cross correlation gives you an estimate, in that you will actually have high variance because you're just predicting one data point at one time, right? Or let me say it otherwise in terms of bias. In terms of bias, it'll be a low bias estimate because you're using all the data for your training. You're kind of using all the data, so it has low bias. No, it's not, you're not going to be talking about so look at it. I think I understand it better in terms of low bias, and not looking at high variance as such. So because you're using almost all the data, it actually decreases bias in your system. And we know that from bias variance trade-off, if your bias is decreasing, you'll have high variance. Fine? Make sense? Yes. So I look at it differently. So actually think about low bias, because more data is used, more data, and this is in comparison of K-fold cross validation. Okay, high variance comparison. This is in comparison. If I've already not said it, from K-fold. From K-fold cross validation. In K-fold, every model is being trained, or every model in every CV iteration is being trained on some K-1 folds, right? So your N by K data points are left for validation. But in your leave one out cross validation, you're using N-1 data points for training, and hence you have comparatively low bias when compared to K-fold cross validation. Think about low bias because more data is used in every CV iteration. Okay. Computationally, obviously, you said that this is very expensive when compared to K-fold cross validation, and it may take plenty of time to cross validate using your leave one out cross validation. So not a preferred method in industry. If you have a lot of computational resources, if you're giants like Google, Meta, Open AI, then probably you will do leave one out cross validation. But I don't think they will also be doing, because they have data set size of like in billions, right? So if you're going to do just one evaluation or one model configuration test on using leave one cross validation, I don't know, the world will end, but your cross validation will not. Hence, you will not use leave one out cross validation, but good from the point of view of a theoretical understanding. This is good as a theoretical concept. And questions can be asked on this leave one out cross validation. Like what happens when leave one out cross validation is used in compared to K-fold cross validation. Okay, fine. Now let's look at the fourth type of cross validation. And this is the last type of cross validation that we're going to see in this particular lecture, or in general about the cross validation. Fine. Any doubts still here? Okay. So let me start with stratified K-fold cross validation. Okay. So stratified is what? Stratified means more strategic. Okay. More informed. Okay. So why is this more informed? So it's actually a variation, stratified K-fold validation. Okay, before I go into this, so this is not mentioned in the syllabus, the stratified K-fold cross validation, but The question was there in the sample paper. If you look at GTA 2024 sample paper, they have asked a question on stratified K-fold cross-validation that we are going to see after this particular topic. So we have to do stratified K-fold cross-validation as well. Okay. Okay. So stratified K-fold cross-validation is actually a variation of your standard K-fold cross-validation technique. It is actually very effective whenever you have a case of target imbalance or class imbalance. Okay. What is the meaning of class imbalance? Class imbalance means that suppose you have cats and dogs. Okay. Now suppose whatever data that I collected has only 100 cats and 10,000 or say 1,000 dog data points. So there is number of data points. Right? In this case, I have a huge class imbalance because my dog's class is 10 times more than my cat class. Right? So if I do a random split, I might land up in a condition where my validation set has like no cats at all, or it has like all the dogs, or like very less number of cats, and it's not equally distributed among the validation set and the training set, right? So now this time what we'll do is, so this can happen. So suppose one fold is such that no cat image is there, right? Is this an issue? Is this an issue? If no cat image is there, all you have is dogs in your validation set in one fold, one of the folds. What will happen? So this is an issue, okay? So this is an issue because what will happen is your class, so you will have only one class is there. Only one class. Oh, only one class you will have. Sorry. One of the validation sets. So this is actually an issue that if you have only one class present in your validation set, and it so happened that your dogs are more, what will happen is your classifier will anyway do better on dogs, right? Because there are more images it is seeing in your training, right? So it's more likely to behave better on dogs. Now, suppose you have just one class in your validation, this will be a biased estimate because you're just estimating on dogs, right? So if your accuracy, suppose accuracy is the measure, though accuracy is not the correct measure. Suppose you have AUC. No, okay, let me talk about accuracy only, right? So accuracy will be what? Accuracy will be 100% probably, or say 90% can happen, right? But if I would have given it a single image of the cat, do you think the accuracy would have decreased? But for, I don't know if you guys have seen this. I am hoping that you have seen. Do you know that we use AUC ROC curve for estimation in imbalanced classes? Imbalanced class data sets. Have you studied this? You've studied this, right? So now there is nothing to compute for the other class in the AUC ROC curve because you have just one class, right? So for that, what will be the value of your AUC? It'll say my AUC is 100% because there's just one class over there in this particular data set. But suppose you okay, so AUC, I see it as from 0 to 1. It's usually a number from 0 to 100, but I calculated from 0 to 1, like divide by 100. So yeah, it will say the AUC is 100, right? But is that a true thing? So usually your model will not do well on cats because you already have a class imbalance. So it's likely to make mistakes on cats. And now because you took this particular validation set where there is no image of cat, Now you are not doing a good estimate. This estimate for this particular fold will be biased, and when you average that out, it will impact your overall performance or overall estimate of your performance. So this is not a good thing to happen, that your one fold doesn't have any of the other class images. So it's a not good thing. Fine. Clear why this is a problem? It can happen that other folds have say 50, 60, 30, and this gives 100, right? So you'll move your, this is, if you take an average of this will move it towards the slightly positive side. This will actually not give you a very good estimate. So this is like say fold 1, this is fold 2, this is fold 3, and this is fold 4, right? So this is not a good estimate because this is incorrect. This is not good. Hence, we try to avoid this kind of imbalance and this kind of issues in your K-fold splitting. And that's where the strategy comes in. So what you do is in splits, you basically ensure that every fold contains approximately the same percentages of samples of each target class as in your whole data set. Okay. So each fold contains approximately the same percentage of the samples for each target class as complete set. Okay, so this is say vanilla K-fold. Okay, so in stratified K-fold, what you'll do is stratified K-fold. If you have, if say cats are 10 and dogs are, say, dogs are 1000. So, and suppose I want to do K is equals to 4. Okay. So your data, how you will split it is, you will create 4 splits of your cats class. So you will create 4 splits here. Let me call it C1, C2, C3, and C4. Here also you will create 4 splits, which will be D1, D2, T3, T4. Okay. What will be the number of data points in each of this? So this will have 25 data points. This will also have 25 data points. This will also have 25 data points. This will also have 25 data points. This will have 250. This will have 250. This will have 250. This will also have 250. Okay. Now what you'll do is you will create fold 1. Fold 1 will be C1 plus D1, which will be 25 plus 250, which is equals to 275 points. Okay. Fold 2 will be C2 plus D2. Fold, and all of them will have same number of data points. C3 plus D3, and fold 4 will have C4 plus D4. Okay. So suppose there were like only 999 images. If 99, okay, let me do it in the next slide, but let me just replicate this. Suppose you had only 999 over here. Okay, how will you do this? So just an extreme case over here. If this comes, so suppose you had 999 images over here. So here you will try to create equal splits. So you will have 250, 250, 250. Here you will have 249. Okay. And this will be 225 plus 249. Okay. So this will be, how much do we have? 274 data points. So they're almost equal. Okay, so this is just a case I was illustrating how do you handle when you don't have equal number of data points in the split. But this is what it is. Okay, so this will also have 275 data points. Right, and we had 1100 by 4, which is nothing but this is what we have, right? So we have 2 over 30, which is 7 and 2 to 5, right? So this is correct. right? So if we would have done our division like this, like create an equal splits over here, then it would have resulted in this 225 points. Now this is how you're creating your folds. Okay, so this is your stratified K-fold cross-validation. Now, in case of regression, by the way, K-fold cross-validation can be used for both regression and classification. In case of regression, what you will do is you will make sure that the mean target value is approximately equal in the folds. So it should not be like, for example, I was telling you in the first example that I had taken, if you have student marks, if you're going to split it like this, now if this is the sorted data, and this is say your y value that you want to predict, right? And these are like student marks. What will happen is if you take this particular chunk, right, you will have high marks over here, right? So this is not a good split. So what you'll do is you will check what is the mean of this particular split. What is the mean of this particular split? What is the mean of this particular split? If they're not almost equal, you will change. You'll split it again such that you will have same or almost equal mean of the target variable. Target is basically your student's marks or y over here. Any y you can take. And you'll try to keep the same mean in every fold. Fine? Clear? Okay. So this is how it is. Fine. So the algorithm is very simple. Now you have to split the data into K parts such that every fold approximately has the same percentage of samples of each target class as the complete class, right? So other way to do it is you split every class equal in equal number of folds and you add the splits or add the folds for every class and make a bigger fold for the whole data set, right? And then you use the same thing that you do for ith data set. Ith fold will be your validation set and rest you will use in training and you will you will compute your validation performance for every fold that you have and you will just take an average of that. Fine, and that will give you a final estimate, a very good estimate of how your model is doing on this imbalanced data set. Fine. Okay, now let's look at in action. So visually, I feel that it helps if you can see it visually. Suppose you have all this data set. Okay, so now this data set is actually imbalanced. You can see, I think I counted the number of. So I think there are 8 dogs and 12 cats over here. Okay, so not sort of a very good imbalance, but sort of imbalance only. So if you do a random splitting of this, what can happen is that this particular fold ends up with no dog images, right? No dog images. And this is a bad thing. This is a bad thing to happen. Here you can see that this dog is there, this dog is there, 2 dogs are there, this is a dog, this is a dog, this is a dog, 3 dogs are there, right? And here you have 2 dogs, fine? So how many dogs are there? 1, 2, 3, 4, 5, 6, 7. There should be 8 dogs. Oh, this is 1, 2, 3, 4, 5, 6, 7. And this is also a dog, sorry. Okay, so 8 dogs are there. Yeah, so this is also a dog. This looked like a cat to me initially. Fine. So 3 dogs over here, and here you don't have any dog, right? So this is a problem for us. So we don't want to do that. So what we'll do is we will balance this out and we'll say we need 2 dogs in every fold and 3 cats in every fold. Okay. So you can see that this is a dog, 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 and every fold now has 2 dogs. Okay, so it's quite balanced in your evaluation as well, right? And this is what usually you will try to do in general whenever suppose you're creating your final performance metric holdout set, right? A test set that I had talked about in the initial lectures, that you actually keep one test set holdout which you don't touch until you have finalized your model. In that particular test set also, you try to maintain this distribution, whatever you are getting in your data set, because then you know how it's, suppose that distribution of the data is actually closer, how your data set that you have received is, if suppose in the world there were actually more cats than dogs, then you would try to ensure that kind of distribution also stays in your test set, on one the set on which you will actually report your final metric. After you have done cross validation, you have trained your final model, right? So in that test set also you will try to maintain this distribution. So if it's on you to create that test set, you always ensure that same distribution propagates to the test set as well. Fine, clear? Okay, fine. So this is your stratified K-fold cross validation. Okay, now let's do some questions. So did I do? So there are similar disadvantages and advantages of K-fold cross validation and stratified K-fold validation only. Stratified is just an improvement over your K-fold cross validation for imbalanced data set. Fine. So this is specifically for imbalanced data set. Fine. Okay. So let's see this question. So this was from GATE sample paper 2024, and this was a 1-mark MCQ. Okay, so the question is asking, a binary classification data set contains only 5% of positive instances. So we know that this is a imbalanced data set. Which of the following experimental design and performance measure is most suited for measuring the generalizability of the classifier trained on this data set? Okay, so they are saying that this particular data set that we are talking about is very heavily imbalanced because only 5% of the data is positive. Rest other is other class, which is probably the negative class, right? Now they are saying that I want to design an experimental setup. How do I evaluate the metric? How do I do the model training, right? And to measure, they're asking to measure the generalizability of the classifier, which is trained on this data set. Which particular design, experimental design and performance measure should you use? Okay, so let's look at them one by one. Fine. So what are the options? They're saying that fixed training and test set accuracy. So fixed training and test set and having an accuracy measure. Fixed training and test set under area under the ROC curve, AUC ROC curve basically, or area under the RC curve. Then they are saying stratified cross validation and accuracy, and stratified cross validation and using area under the ROC curve. Okay, so there are two choices in both the design and the experimental design and the performance measure. Okay, so let's talk about the experimental design first. Experimental design. Okay, so in experimental design, we have a fixed training set, and test set, right? So what is the issue with this? So if we have a fixed training set and test set, we might not get a good estimate because we might not have good split. If the split is bad, we might not get a good estimate. Right? Another issue with this is that not using full data for the estimate. For estimate, test error or test performance estimate. Right? So because of these two reasons, and we know that using stratified cross validation, because we have learned recently, we prefer hence stratified cross validation is preferred, right? First of all, you will ensure that you have a very good stratification. Your class are split equally among all the folds. And then you're using almost all the data set for your test set evaluation, right? So hence you will prefer the stratified K-fold cross validation. Okay. Now let's look at the other option that you have for your performance measure. So performance measure, what is a better option? Performance measured. What is the performance measure? Better. So we have accuracy and AUC ROC curve. Which one is better? So with accuracy, the issue is that it doesn't take care of false positives or mistakes on both classes is not considered. Considered in the sense with the weightage that they have, right? So making two errors on a class which has only 10 points, 10 data points, and making two errors on a class which has like 1,000 points are different things. But accuracy doesn't look at it like that, right? So it doesn't weigh both classes equally. Hence, accuracy is not the correct way to do it. We prefer AUC ROC. This is good for imbalanced data set. Right? And I'm assuming that you guys have already seen AUC ROC in this, right? So hence the option C is the correct one, right? So this is the correct answer, D. Okay. Make sense? Clear, everyone? Why AUC? Again, why AUC ROC and stratified K-Fold cross validation helps? Clear? Fine. Okay. Now let's do question 2. Okay. So you have to tell me which of the statements about cross validation are true. And suppose k is less than equal to n is a positive integer. So there are multiple. So this is an MSQ actually. This is a MSQ, multiple select question. So the question is asking, we have to talk about each and every statement and see which one is the correct option. Okay. So the goal of cross validation is to estimate the training error. Are we estimating the training error? Yes, no? No, we are not, right? So we are actually estimating the test error. Okay, so this is not correct. Repeated application of leave one out cross validation will always produce the same estimation of the error. So what is the meaning of repeated application? Suppose that I have a model configuration that I've fixed. Now I am doing leave one out cross validation multiple times on that. Like I have taken, suppose there are 5 data points. Okay. So this is same model configuration has been fixed. Has been fixed. Okay, so you have fixed your model configuration. Now what you're doing is you are doing say 3 leave one out cross validations. Okay. Do you think the performance estimate that it gives will be same for every run? Every time I do leave one out cross validation? Yes, no. Let's think about what happens in the cross validation, K-fold cross validation. Okay. So this is my CV run 1, in which I'll have fold 1, k is equals to 1. I'll run it for k is equals to 1, k is equals to 2, and k is equals to 3. Right? In CV2, the second iteration of CV, if I do, I can get different folds, right? So k is equals to 1. Say this is fold 1 over here. And this is your fold 1 dash. When you're resplitting your data and you're doing another round of cross validation on the same configuration of your model. Okay. So here, what can happen is these new folds that you create to do the cross validation again, which are like fold dashes and folds over here. Fold 2 and fold 3. So because splitting is random, fold 1 might not be equal to fold 1, fold dash 1, right? So these folds are different. So so let me remove this. I'll do three fold cross validation. So in your three-fold cross validation, what will happen is, suppose I'm doing first round of cross validation where I'm creating 3 splits and I'm running the cross validation. I'm getting some estimate, which is like say CV1. Here I'm running the cross validation again. So I have resplit the data. Now, because this splitting happens randomly, your folds that you create in fold 1 and fold dash 1 will not be same, essentially will not be same. And hence your CV1 will not be equal to CV2. Make sense? CV1 is not equal to CV2. Okay. So what is the meaning of CV1, CV2 here is, this is first run of cross validation in which you are creating 3 folds and you are estimating value for this fold, this fold, this fold, and then you're taking a mean of this and calculating CV1. In this, you're evaluating performance of the 3 folds, and then you are taking a mean of this and you're getting CV2, right? So because you resplit the data in your K-fold cross validation, this error estimate that you're doing, the test error estimate, will not be the same, right? Will it be the case for leave one out cross validation as well? Yes, no. No, right? Because every fold in the leave one cross validation is same because it's just the data point. Hence, even if you do LOOCV again on the full data set, the same folds are there, and hence you will get the same estimate, right? So this is true. As LOOCV has same folds. After repeated application. Fine. So this is correct. Okay. Let me duplicate this. Fine. Okay. So now we have this. Now what about this? Leave one out cross validation is equivalent to K-fold cross validation when K is equal to the number of observations. So this we saw, this is correct, right? So this is by definition correct. So this is by definition. Fine. So this is correct. Now leave one out cross validation is always faster than K-fold cross validation. Is it always faster? No. So this is not faster, right? We saw that there'll be more training examples. So there'll be more training examples in every fold, and more folds, more number of models, and more folds will be there. More folds will be there. Hence, more models will be trained. More models will be trained. Right? So this is not correct. So this is incorrect. For any K, repeated application of K-fold cross validation will always produce the same estimation of the error. So this we already saw in the last slide that this is also incorrect, right? So the correct options from this are B and C, right? And I have given you the explanation for literally every one of them. So this is how this MSQ is. Fine. Okay. Now let's do one more question. So you have to tell me whether this is true or false. In n-fold cross validation, each data point belongs to exactly one test fold. So the test folds are independent, right? And here n-fold or k-fold is same. Are the error estimates of the separate folds also independent? So given that the data in the test folds I and J are independent, we are asking whether the estimates, the error estimates EI and EJ are all of the test folds I and J also independent. True or false? Okay, so so this is false. Okay, and why is this false? This is false because your training data for every fold is not independent, right? So what is the meaning of that? Now let's suppose this is my data set, okay, and I'm creating fold 1, fold 2, and fold 3. Fine. So when I do model 1, like CV iteration, this is in your CV iteration, you're training model 1. Your validation set has fold 1, right? And your training set has fold 2 and fold 3. Fine. In your model 2 training, which is part of your CV iteration, you have fold 2 in your testing or validation, and you have fold 1 and fold 3. Right? Can you see that fold 3 is common over here? Fold 3 is common. Right? So you're using the same training data in both these model trainings, right? So the estimate that you're getting after training your model is not completely independent, because your training data is not completely independent. We would have said that the test error estimation is completely independent if we had like different training data completely, but here you don't have different training data, right? So this is not completely independent. Now in model 3, you have fold 3, which is over here, right? Now you have, what are the folds in your training? You have fold 2 and fold 1, right? Right? So these two also have something in common, right? So they have fold 1 in common, right? And here these two have fold 2 in common. So because we have training data which is common in these model trainings, this is not completely independent, or they're not they are basically dependent on each other, because you're using the same training data to train these different models. Hence, this is false. Clear? Since a data point appears in multiple folds, the training sets are dependent. Even if the test data is independent, the dependency in the training data actually introduces a kind of correlation in the resulting models and their errors. Okay. So if one model is performing bad, the rest of the models are likely to perform bad, as the intersection in their training data is very high, right? So there is some sort of correlation because of commonality between your training data, and you can think of it in this terms, and this helps me in really thinking about that if you know that one of your models is performing bad, then you will know that rest other models will also perform bad, because your training data is quite common, right? You have like approximately only one fold differs in two different model trainings, right? Hence, you know that approximately, I don't know, k-1, k-2 folds are same. So the intersection is huge between two different trainings. And hence, if one model is performing bad, the rest others are also likely to perform really bad. And hence, there is a correlation between the test performance of the first model that you train as a part of your CV iteration and the test performance of the second model that you train as a part of CV iteration. Hence, your test matrix or test evaluation is not completely independent. Fine? Clear? Okay. Now let's do the Fourth question. Okay, so this is also an MSQ. So you have to mark all the statements which are true about cross-validation. Okay. So increasing K in K-fold cross-validation decreases the bias of the model. So does this decrease the bias? Yes, no, true, false. So we saw this already, right? So actually, if you use more data, once you are going to increase your K, let me just replicate here. So here, so more K or say greater K means more training data for every CV iteration, right? And this we saw that you will have more training data for every CV iteration. So if you have more training data, will your bias increase or decrease? It will increase or decrease. What do I have here? So it will decrease, right? So this is correct. Your bias decreases as you add more data to your model training, right? So this is correct. Now, if we use cross-validation, we use cross-validation because it is less computationally expensive than regular validation. Regular validation means hold-out validation. So this regular validation means hold-out validation. Hold-out validation. Right? So we use cross-validation because it is less computationally expensive? No. So we know that CV is more computationally expensive. So CV is cross-validation is more computationally expensive. Hence, this is not the reason why we use it. We use it because it gives us better error estimates than the holdout validation, right? We use cross-validation over regular validation because cross-validation allows us to use the entire dataset, training dataset to the test model, to test the model. This is correct or incorrect? So it's saying that we use cross-validation because it allows us to use the entire training data. Training data means whatever you got as a part of a data set. So this is basically your original data set, which you got as a part of your training data. And then you created splits from that. So we use it because we are able to evaluate our model on the entire training set that we will eventually use after the CV is being done to test the model. So this is correct, right? So this we saw that every data point is part of the test at some point or the other in the CV iteration. And hence we actually evaluate on all the data points, right? So this is one of the reasons we would prefer using cross-validation. Fine. Now, cross-validation cannot be used in production as the model is cheating by looking at the validation samples. We can't use cross-validation in production because model is cheating by looking at the validation samples. So every model training, suppose what this is saying is that, can I use the model? Okay, so let me explain this a little bit more. What is the meaning of this particular statement? So it's saying that, can I use a cross-validated model? Cross-validation as in, suppose I train those 5 models, okay? And I am using, so rather than training another model, after, fixing my all the parameters or configuration that I've learned from this cross-validation, I say that I will use all of these K models that I've used, and I will predict from all of these models, and I'll take a mean or a max vote kind of a thing from each of these models that I've trained as a part of my CV iteration, right? So it's saying that you should not use that model because it's cheating by looking at the validation samples. So actually it's not cheating, right? In training, so cheating would have been if in training you were using the same samples that you were using to test it on, right? So what would have been considered as cheating? So in my CV iteration, what is happening? You have fold 1, fold 2, and fold 3, right? So when I'm doing model 1 training, right? So you have validation and training over here. Here you have fold 1 and you have fold 2 and 3. So cheating would have been if there was some intersection between the validation and the training, right? In fold 1, in model 1, this is not the case. So this is one CV iteration. This is CV iteration, right? This is fold. So there could be multiple meanings of this actually. I'm giving you one interpretation of this. Fine. So here, this fold will be used in fold 2 and fold 1, fold 3 will be used in training. Model. So this fold 3 and this is fold 1 and fold 2, right? So validation and training has no intersection, right? It would have been cheating if you were training on the same data and evaluating on the same data, right? But here you can see clearly that validation and training sets have no intersection at all. Therefore, this is not cheating. Okay. So hence, this particular option is incorrect, right? So the so validation and train are completely independent. Hence no cheating. Fine. So in production setting, and this is what I've done in my experience. So what we actually do is we sometimes don't train a final model after setting everything, like after hyperparameter tuning. Whatever models we have trained as a part of cross-validation iteration, we take the best cross-validation iteration and we use all of those K models. We predict from every one of that K model and we take a mean or some max code kind of a thing for the final prediction value. Okay. So ensembles are not part of the syllabus, but I'll just add this term here. So ensemble means having just not one model, having multiple models and predicting to all of them and collecting their predictions and taking in mean or an average or mean mode or some max mode kind of a thing. So cross-validation can also be used in that terms in production setting, that rather than having just one model, you have model for every kth fold that you have, and you use that as a final model in your deployment. So that's also fine. So there are two interpretations to this. Another thing is that cross-validation cannot be used in production because whatever estimates that you're giving is not correct. But whenever whatever estimate we are giving, in that training and test are very independent from each other. Hence, it's not cheating. Okay, so there are two interpretations to it. One is that you're using those 5-6K models that you have trained as a part of a CV iteration. You're not training a final one model. You are using all of them K models and you're taking a max vote from every model and using it in your final production setting. Here in this, another this thing is that you cannot use CV because it's not a good estimate. It's because it's cheating by looking at the validation samples. So for every model training, it's not looking at the validation sample. For every model training, your trains and vals are completely different. Hence, it's not cheating. Fine. Okay. So another term I will introduce here, something called as data leak. So data leak is when train and val have intersection, right? So if so happened that your training set and your validation set has some intersection, then we say there is a data leak, and then we don't prefer these kind of models. We should not have data leak whenever we are training our models, because test set should be completely independent of what you have trained on or what you have already seen, right? Similar to Gate should not ask you questions that are already there in your PYQs, right? Should not repeat the question because that's not a good estimate of how a person is, right? If the PYQ was already there, it's a high chance that this guy has already been trained to perform well on the PYQ. So if GATE 2024 gives you all the PYQs, like the paper is going to be exactly same as the last year, everybody is going to score 100, right? Hence, we should not use training and validation as same, fine? Or there should be no introduction and validation and training. Fine. So this is the answer. So A is correct and C is correct. Rest B and D are incorrect. Fine. Okay. So this is it for the lecture. So I have attached two videos with, so there are some 7 questions in one video. I think this is video 1 and 5 questions in video 2 after this particular lecture. So please go and watch those 2 lectures. They are in they are in the same lecture series after this lecture. So there I'm solving some 7 plus 5 questions. I think one of the questions I've taken in this particular lecture also. So you'll get approximately 11 questions that you can practice on cross-validation. Okay. So a very easy concept. And I didn't see any question in cross-validation in GATE. So GATE 2024, but something that you can ask easily, right? So prepare it well. It's a very easy topic to understand. No rocket science in this. A simple strategy, simple technique. So just solve these questions. You will get a very good idea of how to use cross-validation with KNN. So a lot of questions you will find are with KNN and cross-validation. So solve that and you will get a very good idea. If you have any doubts, please let me know on Discord. Fine. So that's all for today. I'll see you in the next class. Let me know if you have any doubts.